In this problem, problem number 4, we'll look at a different equilibrium situation, one that involves a very large value of K sub C. Furthermore, the equilibrium involves nitrogen and hydrogen and ammonia, and from the text we're able to see that the nitrogen is initially present with 0.25 moles of nitrogen, 0.50 moles of hydrogen, and 0.10 moles of NH3. Furthermore, we know that the equilibrium constant for this reaction is a very large number, something that tells us that when equilibrium has been reached, as much as possible, products will be present. Okay, so the way to approach this is to realize that we have initial values, initial moles for nitrogen, for hydrogen, and for the NH3. The fact that this is a large equilibrium constant, though, tells us that it favors the products. And as we have a lot of reactants present initially, we know that it's going to have to shift to the right. More importantly, it's going to shift very strongly to the right because our equilibrium constant clearly favors the products. However, we already have some product present, and that's not a problem. The fact that we have so much reactant present is what's driving this reaction to shift to the right strongly, and what we'll be doing is simply adding more to the pre-existing 0.100 moles of NH3 that we've been given to begin with. So we'll be adding to that pile. More product is coming. However, being a strong shift to the right, we won't be able to use the x is equal to 0 assumption. We've got some nasty math ahead of us, and so a material shift is clearly what is in order here as we convert as much of the reactant to product before we begin the equilibrium problem, and this will let us avoid this nasty math and continue working the problem much more easily. So one thing to notice as we examine the initial number of moles of N2 and H2 is that they are not in a 1:3 ratio. Now, our balanced chemical equation tells us that we need one of these N2 molecules for every 3 of the H2 molecules. A 1:3 ratio is what it would take to react nitrogen and hydrogen perfectly together and form product. However, the initial number of moles that we have, 0.25 and 0.5, are not in a 1:3 ratio, are in fact in a 1:2 ratio. And since that doesn't match up with the balanced chemical equation, we know that we've got a limiting and excess situation that we need to deal with. So we'll need to determine a product prediction based upon the nitrogen and a product prediction based upon the hydrogen, and do the necessary analysis to determine which of these is limiting and how much product we can actually form. So beginning with the nitrogen, what we have, 0.25 moles in green there of nitrogen, and we multiply by the appropriate mole ratio that lets us convert moles of nitrogen into moles of the product, NH3. And that mole ratio, taking the coefficients from the balanced chemical equation, is a 2-to-1 mole ratio, and doing the arithmetic tells us that we'll be able to make 0.500 moles of NH3. Well done. Halfway there. Now, let's do the same kind of calculation, beginning this time with the hydrogen. We have 0.500 moles of hydrogen, and we multiply by the mole ratio, again predicting product in this case, where we have 2 moles of NH3 for every 1 mole, or 3 moles of H2, okay, a 2-to-3 mole ratio there, and we do the arithmetic and we predict that we'll be able to make 0.333 moles of H2S. Okay, with these two predictions, we're in a good place where we can decide which one is limiting and which one is excess. The one on top is clearly the larger value, and it is associated with the reactant, which is the excess reactant. And we identify nitrogen as the one that was given to us in excess. The lower value, 0.333, is the one that's associated with the limiting reactant, H2. H2, being the limiting reactant, is the one that is going to be completely used up and will attain a value of 0 as a result of the material shift that we're about to perform. So having made this identification or determination, we also need to figure out, well, of the excess nitrogen, how much is going to be left over after we shift this reaction to the right? So to determine the leftover N2, we'll need to begin with the reactant that was identified as the limiting reactant, the hydrogen in this case. And we'll need to multiply by the appropriate mole ratio that connects the hydrogen now with the nitrogen. And so this is a 1 to 3 mole ratio. And in doing the arithmetic, we're determining that 0.166 moles of nitrogen are actually going to be consumed as part of this material shift that we're going to perform. Okay? What we're also interested in, though, is how much of the nitrogen will be left over, because those nitrogens left over will be part of an initial concentration in our equilibrium problem. So to determine the amount that's left over is quite easy, actually. All you need is the initial number of moles of nitrogen that we had. We subtract that which we've already determined is going to be consumed, and then we determine that 0.083 moles of nitrogen are going to be left over after the material shift. As we continue now with problem number 4, let's recap those things that we know about this problem and the direction that this information is taking us. To solve this problem is going to require information regarding the initial moles that we have, and we were given 0.250 moles of N2 and 0.50 moles of hydrogen and 0.10 moles of NH3. Now, we also know that the equilibrium constant is a very large number, clearly favoring products, which is to say that once equilibrium is reached, about as much product as can be produced will be there on the product side. And the fact that we have so much nitrogen and hydrogen present initially tells us that this is going to be a very strong shift to the right, and that could lead us down the path of some rather nasty arithmetic. So what we're going to do is a material shift, and that material shift is going to require that we know how much to shift and that we know what the final number of moles will be after the material shift. The preceding slide worked through all of that arithmetic as we identified which things were in excess and which ones were limiting. And the hydrogen in this particular problem, as we made predictions for the product, turned out to be the limiting factor. And as the limiting factor, all of the hydrogen is going to be shifted over to the right-hand side, leaving us with none after the material shift. The excess reactant, the nitrogen in this case, not all of it could be used, and we determined previously that 0.166 moles of the nitrogen could be used, leaving us with 0.0833 moles of excess leftover nitrogen. Additionally, as we've converted reactants into products, we've also added to the product pile. And using the limiting reactant, we predicted that 0.333 moles of additional NH3 would be present. Now, avoid a mistake. Frequently, students I find when they're doing problems like this forget about the initial amount of NH3 and then just blaze forward with the 0.333. But the truth of the matter is that the total number of moles of NH3 is really what we need. That is what we get when we add 0.1 to 0.333, which is 0.433 moles. Now, as you can see, we have moved as much over to the right as possible. We have no hydrogen left over, but what we need now for the next phase of this problem are initial concentrations. And so recognizing that it was a 1.50 liter closed container, we take the respective moles here, the nitrogen moles, and divide by 1.5 to get 0.055 molar nitrogen. Doing the same thing for the hydrogen, of course, is rather trivial, as there is none, tells us that there is 0 molar hydrogen, but then for the product species, 0.433 moles divided by 1.5 is 0.288 molar. Now, there is no reactant, no hydrogen reactant on the reactant side. Our material shift has accomplished this. And since the reaction is shifted as far right as possible, the x is equal to 0 assumption is going to be valid, as we'll see with the equilibrium solution to this problem. Having moved as much of the material over to the right-hand side, to the product side, which is where the equilibrium constant tells us it should be anyway, is going to permit us to work this equilibrium problem very simply, in a very straightforward fashion, using the x is equal to 0 assumption. As we continue with problem number 4, recall what we've done up to this point. We recognized the problem as one that would shift strongly to the right in favor of the products, and as such required a material shift. We used the material shift to determine new molar amounts for products and reactants after the material shift, and we used those moles to determine new initial concentrations. These new initial concentrations are used in the ICE problem that we're about to work. We're coming down the home stretch. The initial concentration of nitrogen, calculated previously, is 0.055 molar. The initial concentration of hydrogen is 0. Hydrogen, the limiting reactant in this problem, was completely used up as we performed the material shift to move as much of the reactant over to the product side as possible. Nitrogen was one that was in excess, and not all of it could be moved over to the product side. We also calculated a new concentration for NH3, and that was 0.288 molar. These are the initial concentrations now that we would want to use as we solve the ICE problem. Note that we have a 0 in the problem. The hydrogen currently is not present at all, and all equilibria have to have non-zero amounts for all species. So it's the hydrogen's 0 molar value that tells us the direction that the equilibrium has to shift, and the equilibrium is going to shift to the left. However, because we have such a large equilibrium constant favoring product formation, this shift is actually only going to be a very slight shift to the left, just enough to generate a small amount of hydrogen and nitrogen and attain some kind of equilibrium. The ICE problem is very conventional from this point forward. Why? We know that as this reaction shifts to the left, some amount, X, of N2 is going to be produced. Some amount, 3X, of hydrogen is going to be produced to bring that level up from 0 to some non-zero amount. And these two reactants will be formed at the expense of the NH3, the product, and it'll go down by an amount of 2X. We can combine these changes with the initial concentrations, 0.055 plus X for nitrogen, 3X basically for hydrogen, and 0.288 minus 2X for NH3. And these are the initial concentrations that we have to work with. The law of mass action for this problem is very straightforward. Ammonia is the product, and it's squared. The two reactants, nitrogen and hydrogen, nitrogen appears with a 1 superscript, and hydrogen appears cubed, as there's a 3 in front of hydrogen in the balanced chemical equation. Substituting the values for the equilibrium expressions that we've determined here, our product is 0.288 minus 2X. Our hydrogen reactant is 3X, and don't forget to cube it. And then we also have the nitrogen 0.055 plus X on the bottom of that fraction as well. Now, we've set the problem up in a way that we expect only a very slight shift to the left. And as such, we hope to be able to use the X is equal to 0 assumption. Recall that we can only use the X is equal to 0 assumption where X is subtracted or added to some non-zero value. And so this first location is a prime suspect, a place where we could let X equal 0, and so is in the denominator where X is added to 0.055. This is another place where we can let X equal to 0. Only where X is added or subtracted from some constant value. The 3X in this case can't be touched because it's neither added nor subtracted to anything. Okay, well, this is going to simplify our arithmetic quite a bit. On the top, we'll be left with 2.288 quantity squared. On the bottom, we'll still have the 3x cubed, but we'll have 0.055 on the bottom as well. Okay, and as you can see, this is going to mean no FOIL will be required and quite a bit simpler arithmetic. All of this must be equal to the equilibrium constant, and we'll need to solve that expression for x. I'll leave it to you in your calculator. You'll be using the cube root function of your calculator. Oh, and by the way, don't forget that 3x cubed is actually 27x cubed. So that 3 must be cubed. 3 times 3 times 3 is 27. Be careful about that. In any case, once you solve for x, you should get a value of 5.3177 times 10 to the minus 4th. Take some time and verify that that calculation's been done correctly. We can now finish off problem number 4. We've done the material shift, we've solved the ICE equilibrium problem, and now we can start thinking about what the equilibrium concentrations are. From our ICE problem, we know that the equilibrium levels are given by these three mathematical expressions, and furthermore, we were able to solve for a value of x rather easily with our x is equal to 0 assumption used. And now what we would need to do to finish off the problem is calculate equilibrium concentrations, check the 5% rule to make sure that our assumption about x equal to 0 is legitimate, and then finally use our equilibrium concentrations to determine whether they're correct or not by substituting into the law of mass action. So let's look at these equilibrium concentrations. The initial, or the concentration of nitrogen at equilibrium is given by 0.055 plus x, and if we take our value of x and add that to 0.055, we get a slight increase in the amount of N2 as this reaction shifts to the left. The hydrogen initially present at a 0 molar concentration was what motivated this equilibrium shift to the left, and the amount of hydrogen at equilibrium is 3x, which is equal to 1.59 times 10 to the minus 3 molar. Lastly, the product is what was sacrificed to a very small amount as reactants were made to achieve equilibrium, and 0.288 minus 2x gives us the final equilibrium level of NH3, which is 0.28773, a very small drop in the amount of NH3 that was originally present. So we can say that most of the material shifted to the product side stayed put on the product side. Only a very small amount was used to shift over to the reactant side to create non-zero amounts. And so this is consistent with our equilibrium constant, which told us that as much on the product side as is possible should be what we observe when equilibrium is finally achieved. Only a small change to the reactant amounts is actually observed, small increases to both the N2 and the H2. Both of them are present at low levels. So moving on to the 5% rule check, note that we have used that x is equal to 0 assumption when we determined how we should deal with 0.055 plus x. And that, as it turns out, is very critical in comparison to the other spot where we used the x is equal to 0 assumption. Now, when in doubt, you should probably check the x is equal to 0 assumption 5% rule for both of these. However, looking ahead, I can see that x will probably be a larger percentage of the 0.055 since 0.055 is so much smaller than 0.288. So I name the 0.055 box as being critical, because if that one passes the 5% check, then for sure the 0.288 and 2x will pass the 5% check. But again, if you don't feel comfortable looking ahead and making such judgments on your own, please check both of them to make sure both satisfy the 5% rule check. But I'm going to just do the nitrogen now, as it's the most critical, and I'll take the value of x and I'll divide my value of x by 0.055 and multiply by 100, and I get about a 1%. Okay, so since 1% is less than 5%, I'm happy with that result, and my x is equal to 0 assumptions throughout the problem are legitimate and verified, and I can move on. So to finish the problem off, it's always a good idea to plug the equilibrium concentrations that we calculated into the law of mass action. And if I do that, and you can see these results here, what I get is a value for an equilibrium constant, which is 3.67 times 10 to the 8th, which happily looks very much like the 3.70 times 10 to the 8th. And as these two are in good enough agreement, I can say that I do have equilibrium concentrations and that the problem is actually solved.